So we have the new Larkos model 0.1 with a new working Python frontend in the we currently are in the training loop file. Obviously, we've got the standard forward-backward steps and the side effects which trigger the C backend, of course. Then the emotion pipeline. So, what we can see immediately, except for the comments showing that, I had real problems with this, we can see the usage of the cognitive fuse, or where was this? The fusion transformers, the fusion transformers. As well, it's a bit different than the normal models, you could say. Let's say these are normal. I can't draw, that's certain. So we've got, they mostly work on language comprehenses. So they use language, they use the transformers, and you can't really say that a lot of thinking happens there. I mean, it's mostly just predictions and mapping with the text bridge to the language. So you've got predictions, oh my god, predictions. So here we use a BERT or GP2. I mean, BERT, and here we have language. I mean, you could argue that, over time, the so-called, the default transformer models do develop, some kind of primitive, some kind of primitive intelligence, or maybe they are LARPing that intelligence, but if we take the Larkos 0.1 model, it's a bit different. You also have the standard, you also have the transformers, but the transformers, they more guide the model instead of being the main thing of the model. So, and we also use the neurons from the Larkos. So we have neurons, the average LLM stuff, and memory. And we use the cognitive fuse mechanism to combine those into one tensor. We will get into the math later, but So, what does this actually allow us? This allows us to have a bigger kind of emergence, you could argue. As we have the default things we already saw in Larkos, allowing the bigger bigger debuggability, you could say. So now if I close this, we get to the backend things. The reason why even it's called the backend is because firstly I had this whole C code and the backend stuff on Linux VM, but after some point of time I moved to a Linux server simply, and I just decided to run all of the code, but I kept some things so it will be easier. So we also have the running training loop, so the backend deriving all of those stuff, the decision paths, well, the average Larkos stuff. If you saw the previous video, you should somewhat know what is happening here. So we should now get finally into the fusion mechanism. So if we ignore this stuff and well the projects and stuff, it just allows us to like project the fusions into a more deeper state. We have the main cognitive fuse. So we can see that the text stream also is projected, but I mean this really was an attempt to make the text bridge to work with the whole Larkos. But after some point of time when I saw this wouldn't work, I just decided the text bridge would be a guider instead of a main thing. We also project the neurons here. We do some LLM stuff default. And yeah, that's really it. If now I go into the documents, so if we now go into the PDF files, we can see that a lot of more things will be clear now along with the math. Well, we can see that this, for example, was already in the Fusion code. I think we all saw it, so immediately. And yeah, so this is, well, if we consolidate the whole algorithm into math, this is what the formula looks like. We use Johnson's-Lindström's method to stabilize the dimension, and here we have the projection band. And we have different seeds, so yeah, they don't occupy the same subspace. We'll later normalize everything, as we always should. And yeah, that's it. So now we shall look into the experiments and the main file of the the whole thing. So here we have a full document on it, but we shall ignore this for now, as you already saw it. You can also saw the AI methods used in it, but I mean they are not that interesting. They are rather default. So firstly, what we can see from the experiments, so the actually interesting part, we can see that the loss obviously decreases quite fast. It's true that the dataset wasn't that big, but it's still good. Now, something that actually matters, so domain transfer. So we see if the domain A, so we train on domain A and then we change to domain B and see if the training on domain A will cause domain B to be trained faster. And this has succeeded, as you can see. The test has passed and this was proved. So we can see that domain B trains faster because of it, and transfer efficiency is therefore this. Now we have continual learning. This is just basically a stability test, scalability test, to see if we can actually scale the thing. And yeah, now the discovery test, the one that actually you could say failed because there weren't enough alignment pairs. I mean, all of the normal things passed, but yeah, the alignment pairs are somewhat missing. And what we can immediately see from the graph is over time the fused variance decreases. Well, it collapses, you could even say. And this indicates, of course, insufficient exploration. Admittedly, though, this is quite predictable because, as we said, the dataset wasn't quite big enough, and there really isn't that much to explore in the dataset. It's just so I don't have to train on God knows what. That is said. Here we also have another scalability test, so to see if everything is stable. This passes. Internal world model, so another interesting thing. So we want to see here if the model creates its kind of language, you could say, or word, well, really language. So as we can see, you could say vectors do consolidate into higher dimensionality. They do not collapse into some manifolds, so this generally passes. Adaptation speed, so how fast does the model actually adapt? How this work would be was we would have some rules, we would change one rule and would see how much it would adapt. So we can see that here loss quickly rises and then it quickly decreases. So this test succeeded. And now meta-learning test, so another interesting test. And we can see that the loss curves across the three meta-learning phases, they all start from a lower initial loss. So here we start above 0.5, here we start around 0.3, and here we start below 0.3. And they all decrease, as you can see, and this indicates that the model is in fact learning to learn. Not exactly by a high margin, but with scalability, this margin should increase. Now we also have affective representation, so we want to see if the model consolidates its, well, the simulations of the emotions into higher states, you could say, more complex states. This isn't because we want in AI, well, emotions, we obviously don't, but this was basically a test which I thought would very good see if, well, there was some higher emergence in my opinion, and it also passes. So yeah, we have the 77% loss reduction, we've got a good efficiency in domain transfer. Well, this is true, the loss trend warnings are well, margin, but admittedly we didn't train on a big enough parameter model. It was around 200,000 maybe, something along those lines. So yeah. We also have the emotional things, the identity things. Yeah. Now if we go to the testing file, you can see how these were implemented. So they were pretty much just asserts, but working asserts nonetheless. So what can we... wait a moment. What can we actually conclude from all of this? Well, we now know that the Larkos model can be scaled using, well, Python and C types. We know that the Larkos model can indeed show higher forms of emergence, you could call that. We know that the cognitive fuse mechanism works. We know that the affective system and the hidden inner genuine affect works, which was a concern for a time because I wasn't quite sure if the emotion system was working, but well, it is. That doesn't mean the model is, well, feeling any emotions, but it does, well, emotions have their uses somewhat, and we use the uses we need, you could say. Here we also have the interference thing, so we just freeze the weights and run the forward steps. That's pretty much it, what we can all conclude.